Hello everyone, welcome to this video. In this video, we will be studying about law of exponents for abelian groups. So this law tells us that if we have some abelian group and n is any integer, it could be any integer, plus, minus, it could also be 0, then we need to show that ab whole raised to power n, that is equal to a to the power n and b to the power n. This is basically the law of exponents, and we have to show that this thing is true for all the abelian groups. That means we need to provide a proof for this. Also, they are asking, is it true that if we take any non-abelian group, then also we have this condition or this property or not. So let's look at the proof of this result first, right? So to prove that, what we wanted to prove that ab whole raised to power n is equal to a to the power n, b to the power n, correct? Where what is n? N is some integer. Now we will try to prove the result using induction. Whenever n is greater than equal to 0, we can use induction because induction is used on positive integers, right? So for induction, we'll go step by step. So we let n is equal to 0 because we start from 0. If n is equal to 0, then your left hand side becomes what? It becomes ab raised to power 0. So basically it is the identity of the given group. And what does your right hand side becomes? It would be a to the power 0 and b to the power 0. So it would be e multiplied with e. And what is that? It is e only. Hence in this case we have left hand side is equal to right hand side. Hence the result is true. Hence the result is true for n is equal to, the result is true for n is equals to 0, correct? What about the second part? In the second part, we assume that the result is true for n is equal to k. If that is so, then we would have a raised to power ab raised to power k, that is equal to a to the power k and b raised to power k. Let's mark this as equation 1. Next, in the third case, we prove that the result is true for n is equal to k plus 1, right? So that means we need to show that is to prove that a to the power ab raised to power k plus 1, that is equals to a to the power k plus 1 and b to the power k plus 1. So let's mark this as equation number 2, right? So we take first of all the left hand side of it. It would be ab whole raised to power k plus 1. So you can write it simply as ab raised to power k multiplied with ab raised to power 1, right? There is no issue. So now we can make use of equation 1 and we can write ab whole raised to power k as a to the power k and b to the power k, right? And this ab would be as such. Why this is so? Because we are using equation number 1. Right now, what we can do, we can make use of the associative, not the associative property, that is not required. We can directly make use of the abelian property of the group, as the group is abelian, right? So we can make use of this property that ab is equals to BA, so that now we can make use of associativity to combine these elements, right? So this is according to associativity, correct? So when you combine these elements, it would be a raised to power k, b raised to power k plus 1 and then a. Again we can write it like this, right? And you can again use the abelian property to write it like this, correct? And then it would be a to the power k plus 1. Again you can use associativity to write it like this, So this thing would be equal to a to the power k plus 1 and b to the power k plus 1, which is nothing but equals to your right hand side. Hence the result is also true for this case, and this was there when your n was greater than or equal to 0. Now let's take the case when n is less than 0. When n is less than 0, we can write our identity as ab raised to power 0. There is no issue, correct? So this would, for the power 0, you can write it like this, n minus n. So it would be ab whole raised to power n and ab whole raised to power minus n. Now you can use part A because for n positive you can use this result. You can use the above result here to write it like this, a to the power n, b to the power n whole raised to power minus 1, correct? And then it would be equal to using the above result, and this would further be equal to ab raised to power n, a raised to power, it would be b raised to power minus n, right, and a raised to power minus n. Why? Because we are using the sock shoe property as ab inverse is equals to b inverse a inverse. So using this property here, we are writing it like this, so that it is further equal to ab raised to power n. Here also we can apply the commutative property to write it like this, right, using commutativity. So it further becomes equal to this thing, right? And what we need to show from here, what do we obtain? We obtain E is equals to ab raised to power n, a raised to power minus n, b raised to power minus n. So we can post multiply on both sides with b raised to power n, so that it would be equal to ab raised to power n, right? And then you can post multiply it with, or actually there is no need to do all of this. Why? Because you can directly do it from here. So let's see, what do we have? From here you obtain this term, that E is equals to a to the power n, b to the power minus n, a to the power minus n, right? So you can post multiply with a to the power n on both sides, so that it would become this, right? And again you can post multiply on both sides with a to the b to the power n, so it would become like this, and this is what you wanted to prove, hence the result. You have another way to do this thing also. Let's see that another way. In this we can directly prove it. How? If we take this a to the power n, so it could be written as ab, and so on up to how many times? In total n times, correct? Now what you can do, you can make use of the associative property to write it like this, right, and so on. This, if you write the last term here also, it would be b a and then it would be b, right? And this is how many times? This is n minus 1 times. Now what you can do, you can make use of the commutative property, because your group is what? It is given to be abelian. So using commutativity, so that it would become a square, and you are left with ba, and so on up to ba, right? And it is b square. You can combine these elements. You can write ab here using this ba here. You can write it like this, right? So that now how many such ba are there? N minus 2, right? So therefore you can continue in this manner. So you see, in total you are having what power? 2 plus n minus 2. So in total you are having n power. Here we have 1 power, so it is n minus 1. So here you only have n times, right? So the total power will remain the same, that is n. So if we continue in this manner, let me show you one more thing here, one more step here, so that it would be equals to a square AB and so on, AB into B square, and this is how many times? N minus 2 times, correct? Next you can again combine the club, so it would be A cube, it would be BA and so on. How many times? B cube, it would be N minus 3 times, right? So you can continue in this manner with the same reasoning over here, so that you would obtain a what? This would be equal to a to the power n, b to the power n, right? And hence we have a result as ab whole raised to power n is equals to a to the power n and b to the power n. So the next question that they are asking to us is it also true for any non-abelian group? The answer is no, because in the proof we have used this property of abelian. If this property is not there, we cannot write it like this. So the answer is no, we cannot write the result, we cannot write the result a b raised to power n is equals to a to the power n, b to the power n for non-abelian groups, right? So I hope you understood this question well. That is it for this video. Thank you for watching.